Welcome to the third video to describe our answers to paper 2 of our April exams. This is going to be questions 5 and 6. Question 5 deals with a microwave source, some metal plates, a couple of gaps. Looks like it's a double slit experiment type device. We have a detector and we've got central maxima, second order maxima. So in this case our second order maxima, so therefore n equals 2. And we want to just kind of analyze this a little bit. As the detector is moved from A to B, a series of maxima and minima intensities are detected. Fine. Explain the formation of the intensity maxima. So when you have constructive interference, you have a bright spot or a maxima, and then when you have and those take place at intervals of when the path difference is some integer of the wavelength. So for example, and this being our second order maxima, it's going to be, our path difference is going to be 2 times the wavelength. And the path difference being the path difference from this point to this point. So this is, we could call this path 1 and this path 2. The difference between there is going to be 2 times lambda. Okay, so the measurements of the distance from each gap and the second order maxima are shown in the diagram above. Calculate the wavelength of the microwaves. So if we use that idea of the path difference, and we take path 2 minus path 1, and we say that that is 2 times our lambda, well then it's a fairly straightforward calculation. So we're going to have 282 minus 204 equals 2 times lambda. 282 minus 204 is going to give us 78 equals 2 lambda. Therefore, lambda equals 39 millimeters. Seems like a pretty reasonable answer for our microwaves. Next question then is kind of a conceptual question. What happens now that the two gaps, the distance between the two gaps are increased? This is a question that deals with the amount or the understanding of the equation. S equals lambda, wavelength, d, distance to the screen, and small d, the gap distance. So and the question is, what happens when this is now increased? So thinking back, if I increase my denominator, what's going to happen to my answer? So an increase in the denominator is going to cause a decrease in my distance between the second order maximas. So therefore, we could say that an increase in gap separation will cause a decrease in distance of maxima. Okay, so in that problem it looks somewhat intimidating when you first look at it, but in reality explain formation of the maxima, path difference, and then just a conceptual understanding of what's going on in the equation. Okay. And finally, question number 6. Looks like we have a couple of pipes, so we're looking at harmonics and standing waves. So we want to kind of look at what's going on here. If we have So pipe A is open and pipe B is closed. So that kind of gives us a... On the diagram, draw lines to represent the waveforms of the first harmonic for each pipe. So the first harmonic of an open wave is going to be something like this. And for our closed pipe, it's going to be, we're going to have a node here, so, and an antinode here, so we want to kind of make sure that that's drawn appropriately. And then, so there are two waveforms. On the diagram, label the position of a node with the letter N. And an antinode, a position of an antinode with the letter A. Okay. The frequency of the first harmonic is 512 hertz. Calculate the length of pipe A. Well, if I know that this is my first harmonic, I know that this that the length of this L is going to be 1/2 of a wavelength. So, if the speed of sound in the air is 325 meters per second, and the frequency is 512 hertz, then I want to be able to find what is my wavelength. And doing some quick calculations, we get a wavelength of 0.635 meters if I use V equals F lambda. So, calculating the length of the pipe, if lambda is 0.635 meters, then if L equals 1/2 lambda, and lambda is then the length of the pipe must be 0.317 meters. B2, suggest why pipe organs designed to emit low frequencies, fundamental notes such as 32 hertz, are often closed at one end. As we can see, if this is half a wavelength, then the length here is 1/4 of a wavelength. So if it's 1/4 of a wavelength, then in the same distance, we have a little bit more pipe to work with. So if I have 32 hertz, and if V equals 325 meters per second, I have a frequency of 32 hertz. Then my wavelength is going to be approximately 10 meters. Well, if I have a pipe that's 10 meters long, that's quite unwieldy. So if I use an open pipe, then my pipe has to be 5 meters. However, if I use a closed pipe, then my pipe only has to be approximately 2.5 meters, which is much more manageable within the confines of a building. Okay. If you have any questions, please leave them in the comments below. Thank you.